Hi, welcome back. In this video, we're going to learn all 6 trigonometric derivative formulas. Remember, there are 6 trigonometric functions, and they all have a derivative. The first 2 you've already seen. The derivative of sine of x is equal to the cosine of x, and the derivative of the cosine of x is equal to negative sine of x. And now, starting with these 2, we can get the derivatives of the other 4 easily. Because remember, all of the other 4 functions can be written in terms of sine and or cosine using the reciprocal identities or the ratio identities. For example, let's find the derivative of the tangent of x. We do that by rewriting the tangent of x using a ratio identity, and we rewrite it as sine of x over cosine of x. And now we can use the quotient rule. So the quotient rule says the derivative of sine x over cosine x is going to be the bottom times the derivative of the top, which is cosine of x, minus the top times the derivative of the bottom, all over the bottom squared. And that looks like a complicated function and a difficult one to remember, but actually we can simplify it. Look at the numerator. In the numerator, we really have cosine of x squared, or cosine squared of x, plus sine squared of x. And all of that is over the cosine squared of x. And now the numerator, using the Pythagorean identity for trigonometry, the numerator is just 1. And now 1 over cosine squared, using a reciprocal identity, we could rewrite that as just secant squared of x. So that's the derivative of the tangent function. It's just secant of x squared, or secant squared of x. All right, let's see the other 3. So here are all 6 trigonometric derivatives. Now, you're going to have to memorize all of these because you don't have time to look these things up. You've got more important things to do. You need these derivatives to do other things. So to help you remember them, you want to look for some patterns. So for example, the derivatives of all of the co-functions, so the cosecant of x, cotangent of x, and the cosine of x, notice those all have minus signs in front of them. And also notice the patterns. The derivative of the cosecant of x looks very similar to the derivative of secant of x. Notice the pattern. The derivative of secant of x is secant x tan x, but the derivative of cosecant of x is negative cosecant x cotan x. All right, so we're going to have to remember all of these so we can do more interesting problems. For example, this problem. If f of x is equal to 4x minus tan x, where x is between negative pi over 2 and positive pi over 2, find f prime and f double prime. So we had to restrict the domain of our function because remember the tangent function has vertical asymptotes at all those places, negative pi over 2, positive pi over 2, negative 3 pi over 2, positive 3 pi over 2. So we just restricted to one of those intervals to look for the derivatives. So let's get the first derivative. The first derivative, f prime, we're going to differentiate f of x term by term. So the derivative of 4x is just 4. Now the derivative of tangent of x we just saw is secant squared of x. So that's the first derivative. Now to get the second derivative, we have to differentiate that. So we know we're going to differentiate the constant 4, and that derivative is going to be 0. But how do we differentiate secant squared of x? Well, remember secant squared is just the secant x times secant x. So we're going to have to use the product rule on that. We don't have any other rule that will give us that derivative yet. After this section, we'll learn the chain rule, and it'll make it easier. But for now, we got to use the product rule. All right, so let's differentiate f prime to get f double prime. So remember, it's going to be 0 minus, and now the derivative of that product is going to be the first times the derivative of the second, and the derivative of secant is secant x tan x, plus the second times the derivative of the first, which is secant x tan x again. And then to simplify this, we notice, we have secant squared x tan x plus secant squared x tan x, and it all has a minus sign in front of it. All right, that's the derivative of the first derivative, and it's called f double prime. So now let's see why these make sense. Let's look at their graphs. So checking out their graphs in Desmos, if we look at the red curve, that's the function f, we see that we have a horizontal tangent line over there, somewhere between negative pi over 2 and negative pi over 4. There's a horizontal tangent line. And we look at f prime, the derivative of f, and we see that f prime is 0 at that same point. And that makes sense because f has a horizontal tangent line. The slope of its tangent line is 0. So the derivative better be 0 there. Also notice that the slopes before that point, the slopes of the tangent lines to f are all negative. All the slopes are negative over here. From negative pi over 2 up to that point, the slopes are negative. Well, look at the y-coordinates on f prime. Those y-coordinates are all negative there. Then the slopes on f, the slopes of the tangent lines to f, become positive from that point between negative pi over 2 and negative pi over 4, all the way over to this other point where it turns around. The slopes are all positive there. Notice that f prime, all the y-coordinates of f prime are positive there. And we have another horizontal tangent line. So f has a tangent line with slope 0 right there. Well, f prime goes through the x-axis right there. So f prime is 0 at that point. Now look at the graph of f prime. It has a horizontal tangent line right there when x is equal to 0. And look at its derivative, the green curve, f double prime, that's the derivative of f prime. It goes through the x-axis there. Also notice that f prime, if you look at the slopes of the tangent lines from negative pi over 2 all the way to 0, from x equals negative pi over 2 to x equals 0, the slopes of the tangent lines are all positive. But they're getting less and less positive. Their slopes are decreasing. They're positive but decreasing until finally they're 0 at x equals 0. Well, f double prime is positive. The y-coordinates are positive, but they're going down. They're decreasing until the y-coordinate is 0 right there. Now, f prime has negative slopes over here from x equals 0 to x equals positive pi over 2. The slopes of the tangent lines to f prime are all negative and becoming more and more and more negative. Well, if you look at f double prime, the y-coordinates are negative and they're getting lower and lower and lower. They're decreasing. So we can see that the graphs help us understand that we got the correct functions for the first derivative and the second derivative. So that's how to use the formulas and how to verify that you got the correct derivatives by looking at the graphs. And I'll see you in some other video.